Can we find the rate of change of an integral without calculating it first? Is it legal to force a derivative inside an integral sign? Physicist Richard Feynman famously popularized a technique for doing exactly this to bypass seemingly unsolvable calculus problems, earning it the colloquial title of Feynman's trick. To understand how this works, we start with the fundamental theorem of calculus. In a single dimension, integration and differentiation are inverse operations. They effectively cancel each other out. The problem arises when a function contains two variables. If we only integrate with respect to one of them, the second variable gets trapped inside the integration process. Conquering this two-variable problem expands the fundamental theorem of calculus into higher dimensions, providing a way to find the exact rate of change for systems defined by accumulation. To see how this maneuver actually works, we need to look at formal mathematical analysis. Walter Rudin's text provides the strict logical conditions required. The exact rules for this are laid out in Chapter 9, which deals with functions of several variables. Pulling a derivative inside an integral is a significant mathematical leap. You are asking permission to swap two separate limit operations, the limit of a difference quotient and the limit of a Riemann sum. We will establish the precise topological conditions that make swapping these operations mathematically legal. Without strict continuity constraints in place, assuming you can just swap limits will yield contradictory, false results. Let's visualize a smooth surface defined by two variables. We have a three-dimensional space where the height, z, is determined by a function of a spatial variable x and a parameter t. Taking an integral of this function means fixing our parameter t at a specific moment, which effectively slices the three-dimensional surface to create a two-dimensional curve. We then calculate the accumulation under this specific cross-section, restricting our area between two spatial boundaries, A and B. This accumulated area is a single number. If we do this for every possible slice along the t-axis, we create an entirely new function, which we'll call phi of t. The spatial variable x is consumed in the calculation. It acts as a dummy variable. The total area of any given slice is dictated entirely by where we place our free parameter, t. To find the derivative of this new area function, phi, we have to apply the standard limit definition of a derivative. We need to see how the area changes when we move slightly forward along the t-axis. We take a second slice at t plus delta t. This visual representation shows our algebraic difference quotient. The gap between these two slices represents the change in area over our small step, delta t. As we shrink that step size to 0, we must consult Rudin's theorems. Theorem 7.17 dictates that we can only safely take this limit if our sequence of functions converges uniformly. Uniform continuity of both the function and its partial derivative ensures that the limit operations are interchangeable, satisfying the formal requirements for the Leibniz Rule. The scenario becomes more complex if the bounding walls of our integration, a and b, are also moving as functions of our parameter t. To find the rate of change for this dynamic area, we track three distinct elements. First is the vertical morphing of the surface itself, calculated by integrating the partial derivative with respect to t. Second, we account for the area gained by the moving upper boundary, which adds a vertical strip to our total accumulation. Third, we subtract the area lost if the moving lower boundary cuts into our region. The multivariable chain rule unites these three geometric changes. It combines the surface deformation with the boundary shifts to completely define the rate of change for the entire dynamic system. Look at this equation. We want to find the derivative with respect to t of the integral from t to t squared of sine of x times t over x. We first verify that the integrand is continuous and has a continuous partial derivative for strictly positive bounds, satisfying Rudin's criteria for limit swapping. We bypass the outer integral and push the derivative inside. Taking the partial derivative of the integrand with respect to t leaves us with the integral of cosine of x times t. Next, we calculate the boundary changes. We evaluate the original function at the upper limit, t squared, and multiply by its derivative, 2t. Finally, we subtract the function evaluated at the lower limit, t, multiplied by its derivative, 1. Finding the explicit antiderivative of sine of x times t over x is mathematically impossible. Differentiating under the integral sign was the only valid path to a solution. In thermodynamics, the Leibniz Rule is the mechanism behind the heat equation, which allows physicists to model thermal diffusion over time. It enables statisticians to calculate generating functions, which track the moments of complex probability distributions. In theoretical physics, this exact operation is required to normalize quantum wave functions and calculate particle probability states. Parameterized integrals form the mathematical language required to model continuous, evolving physical systems across almost every discipline of applied science. To review, integrals over a dummy variable create new functions defined entirely by their remaining parameters. Swapping the limits of differentiation and integration is strictly governed by the Leibniz Rule, which demands uniform continuity. And if the boundaries of your integration are moving, the multivariable chain rule accounts for the geometric expansions and contractions. Differentiation of integrals demonstrates the deep relationship between accumulation and change. It extends the fundamental theorem of calculus into the study of multidimensional systems. If you enjoyed this detailed explanation of Rudin's principles of mathematical analysis, don't forget to like this video, subscribe,